Good day everyone, and hi Miss Sam, our respected physics lecturer. Before we begin our presentation on Hooke's law, we would like to start with a short video. This video offers a unique perspective showing how the concept behind Hooke's law can also be related to human experience in everyday life. Let's take a look.
Imagine holding a string between your fingers. You pull it gently and it stretches, but the moment you let go, it snaps right back. No hesitation, no complaint. Just a quiet return to its original shape. This is Hooke's law in action. It tells us that when force is applied to a spring, it stretches in proportion to that force. But as long as it's not stretched too far, it always returns, always. Now think about life. Every challenge you face, a failure, a setback, a tough day, is like a force pulling on you. At times, the pressure feels overwhelming. You might feel stretched, thin, tested, pushed to your limits. But just like a strong spring, you are built to recover. You are built to bounce back. But here's the key. Every spring has an elastic limit, a point where too much force can bend it permanently, and we do have limits. That's why resilience isn't just about enduring hardship. It's about knowing when to race, when to adapt, and when to let go of things that pull us too far. So the next time life stretches you, remember this. You are not broken. You are not stuck. You are spring, waiting to snap back, stronger, wiser, ready to rise again. Because no force, not failure, not fear, not even the hardest of days can keep you from returning to the person you are meant to be. Be resilient, be unstoppable, be the spring that always comes back. Thank you.
That video gave us an interesting way on how to look at Hooke's law, not just as a physics concept, but also something that we can relate into our real life. To understand this better, we carry out a simple experiment to observe the relation between force and extension.
By the way, this is our group member, consists of 3 cute girls: Natasha, Armida, and Shazila.
The objective of this experiment is to verify the accuracy of Hooke's law. Before that, let's get to know the person who came up with this idea of Hooke's law. He is Robert Hooke.
Robert Hooke was born on 18 July 1635 in Freshwater, Isle of Wight, England. He died on 3 March 1703 in London. He was an English physicist who discovered the law of elasticity known as Hooke's law, and who did research in a remarkable variety of fields.
Before we begin the experiment, it's important to understand the basic theory that supports it, which is Hooke's law. Hooke's law states that for relatively small deformations of an object, the displacement or size of the deformation is directly proportional to the deforming force or load. Under these conditions, the object returns to its original shape and size when the force is removed.
Now let's move to the relationship between force and the change in length or extension of the spring. The F is directly proportional to the change in length of the spring. Mathematically, we write it as F equal to Kx, where K is the spring constant.
To conduct the experiment of Hooke's law, the materials that we need is spring, slotted mesh, meter ruler, and retort stand.
Next, I will continue with the procedure. In this experiment, we investigate Hooke's law by following a series of steps. First, the mass of the hanger was measured and recorded. Using the formula W equal to mg, we calculate the weight of the hanger and recorded it in the data table as W. Next, we adjusted the scale so that the pointer on the hanger was positioned near the upper end of the scale when the load was applied. This initial position was recorded as x0. After that, we add a 10-gram mass onto the hanger and recorded the new scale reading as x1. The load was then increased by equal increment until we obtained 8 data points, ensuring that the pointer did not reach the lower end of the scale. For each added mass, we record both the weight and the scale reading. Once the maximum load was reached, we reverse the process by unloading the same masses step by step. The new scale readings for each removed load were also recorded. Now, let's proceed to the next part. This is our experimental data for Lab 5 Hooke's law. The aim of this experiment is to investigate the relationship between force and the extension of a spring when different loads are applied. In this table, we have several important columns. First, we have the load mass starting from 0.05 kg up to 0.40 kg. Then, we add the mass of the hanger to get the total mass. For example, 0.066 kg, 0.116 kg, and so on. Next, we calculate the weight of the total mass using the formula W equal to m times g, where g is the gravitational acceleration, 9.81 meters per second squared.
After collecting the data, we plot a graph force versus extension of the spring. From this graph, we can illustrate that the force is directly proportional to the extension of the spring. And we know that the gradient of this graph represents the K constant.
Now let's move on to the discussion. From our observation, we found that the extension of the spring is directly proportional to the force applied, as long as the elastic limit is not exceeded. From a graph force versus extension of the spring, the slope represents the K constant. From our graph, it can be seen that the graph obtained is a straight line and is passed through the origin. This means that force is directly proportional to extension until the spring reaches its elastic limit. From the graph, the average percentage error between the experimental data and the base fit line that passes through the origin is approximately 40.96%. Since the percentage error is quite high, there are several sources of error and precaution that must be taken. There may be several sources of error in this experiment. First, they may be due to the random errors, such as the reproducibility of the extension by different students and parallax errors while taking readings. Second, an excess addition of weights causes an increase in the deflection until a point where, for our case, the elastic limit was reached. Third, the spring swinging due to air resistance during taking the readings. Fourth, the reading taken by different person make the data will be less accurate. Fifth, the ice is not perpendicular to the meter rule while taking the reading. In order to obtain more accurate and reliable results, several precautions must be taken during the experiment. First, your eyes must be perpendicular to the scale in order to minimize parallax error. Second, make sure to take the reading 2 or 3 times to increase accuracy. Third, ensure the experiment is conducted in an environment with minimal air resistance to prevent the spring from swinging and allow it to oscillate only along the vertical axis. Fourth, the person who adds the mass to the hanger must do it gently without stretching the spring to avoid exceeding its elastic limit.
Based on the experiment that we conduct, we know that the spring obeys the Hooke's law. This is because the extension of the spring is directly proportional to the force applied to it within its elastic limit. This relationship is mathematically expressed as F equal to Kx, where F is applied force, X the extension, and K is the spring constant. However, the accuracy of the result is only 50.94% and the percentage error is 40.96%.